The world without light is life without love. This video presents the emission, propagation, and reflection of light as mechanical phenomena in the absolute frame and an inertial frame. The study of the emission, propagation, and reflection of light is based on that of massless balls. The mechanical velocity v is the same as that for massless balls. The emitted velocity c replaces the velocity capital V of the balls. The figure illustrates an identical light source and reflecting mirror at rest in the absolute and an inertial frame. The source and mirror have the same geometry. Each source is at the origin of its frame. In the absolute frame OXYZ, the source at the origin O emits a wave front at velocity CE at an angle A from the axis OX. After time t1, the wavefront is at point A of the mirror M. At point A, the wavefront is reflected at velocity CR, then travels the path AB in time t2. The velocity CE and CR have the magnitude c. The light travels lengths OA and AB in time t equals t1 plus t2 at speed c, wavelength lambda, period t, and frequency f. The inertial frame O'X', Y'Z' travels at velocity v, and the source is at its origin O'. Points A and B and origin O' belong to the inertial frame, and their instances in the absolute frame receive a corresponding index. The source emits a wavefront at the velocity CE in direction O1'A1, which is at the angle A from axis O'X'. The wavefront travels on the propagation path O1'A2 at the propagation velocity CSA, given by the vector sum of the emitted velocity CE and source velocity v. The velocity CE does not change its direction O1'A1 and magnitude c along the path O1'A2. At point O2', the wavefront is at A2. It has traveled the path O2'A2 at speed c, E equals c in time t1, and the direction O2'A2 makes angle A from axis O'X'. Path O2'A2 is path O'A in the inertial frame, which is identical to OA in the absolute frame. The wave's wavefront emitted in the direction O1'A1 at point O prime, between O1 prime and O2 prime, are on path O2 prime A2. At point A2 of the reflection, the mirror perceives only the direction and magnitude c of the emitted velocity ce, because the wave front and mirror have the same velocity v. The incident and reflected angles b are measured from the normal to the mirror at the collision point to the incident velocity ce and reflected velocity cr. After reflection, the velocity v keeps the wave front moving in the same direction with the same magnitude v. The wave front travels on the propagation path A2B3 at the propagation velocity CRA, given by the vector sum of the reflected velocity CR in the direction A2B2 and source velocity v. The velocity CR does not change its direction A2B2 and magnitude c along path A2B3. At point O3 prime, the wave front emitted from O1 prime is at B3. The direction O3 prime A3 makes angle A from axis O prime X prime. The wave front has traveled the path O3 prime A3 equals O prime A at speed CE equals c in time t1, and the path A3B3 at speed CR equals c in time t2. Path A3B3 is the path AB in the inertial frame identical to that in the absolute frame. At point O3 prime, light has traveled the path O3 prime A3 equals O prime A and A3B3 equals AB in the time t equals t1 plus t2 at speed c with wavelength lambda, period t, and frequency f, as in the absolute frame. A local observer at point A observes the light coming from the origin O prime, and another at point B observes the light from point A. The kinematics of light makes the difference between the emission and propagation of light. Maxwell's equations give the instant light speed c, which is a universal constant emitted by a source concerning the source at rest or in motion in the absolute frame. When the source is at rest in the absolute frame, the waves travel at the emission speed c with wavelength lambda, period t, and frequency f. When the source is in motion, the waves emitted in the absolute frame at the speed c inherit the source velocity v of mechanical nature, and according to the ballistic law, the propagation of light speed in the absolute frame is given by CSA equals C plus V. In the inertial frame of the source, light travels at speed c with wavelength lambda, period t, and frequency f, as in the absolute frame. In the inertial frame of a source, a mirror at rest perceives only the emitted directions of the waves that are then reflected accordingly. The reflected waves inherit the source's velocity, such that in the source's inertial frame, the reflected waves are like when the source and mirror are at rest in the absolute frame, having the same speed c, wavelength lambda, period t, and frequency f. The ballistic law, applicable to massless balls and light, is embedded in mechanics because it is derived from mechanics. It works in the absolute frame that is the background of any source's inertial frame, and works on each massless ball and light wave emitted by a source in motion, creating in the source's inertial frame a phenomenon identical to that in the absolute frame. Therefore, the kinematics of light explains and confirms the principle of relativity, according to which no experiment in an inertial frame can prove its motion. It also explains why the laws of physics have the same form in each inertial frame, and why the speed of light is the constant c in inertial frames where the source and reflected mirror are at rest. It is convenient to compare the physics phenomena from inertial frames with those in the frame at absolute rest, which is an inertial frame at zero speed. The phenomena in each inertial frame are similar to those in the frame at absolute rest. Therefore, each inertial frame can be considered a local frame at absolute rest for phenomena belonging to that inertial frame. The study of a physics system belonging to an inertial frame can be performed in another frame, considered a stationary frame or a local absolute frame, where the inertial frame travels at the relative velocity between the two frames.